All right, so when we look at molecules, we want to be able to predict its properties from its structures. And in this case, we're talking about acid-base reactions, which is going to be our transfer of our H+. And so we want to predict what part of a molecule is acidic or basic. And so we need to know what the products look like. And so for relatively simple compounds like ammonium, NH4+, right, all of these protons are the same. And so it's relatively easy to predict, right, that one of these equivalent protons is going to get ripped off. And then the electrons from that NH bond are going to turn into a lone pair to form your NH3 or ammonia. And then your BH, right, where B is just some kind of generic base. And so that's relatively simple because it's a relatively simple molecule. What about more complex molecules? And so when we have more complex molecules, we have different types of protons that could be acidic or different sites of the molecule that could be basic. And so in order for us to predict which part of the molecule is going to be acidic or basic, we have to know what the conjugate acid or base would look like. So let's take a look at acidic compounds first. And so in this case, we need to know what the conjugate base looks like. So let's go ahead and take a look at this relatively simple molecule and start analyzing how this thing would interact with some kind of base, right? So we're going to add some kind of base to this, and the base is going to take away a proton. So you have to remember your reaction mechanism here, right? The base is going to take off a proton and then leave a lone pair behind. And in this case, it might be a negative charge. So remember that there's a proton over here. There's a proton over here. And then there's a proton over here. Remember, the central carbon has no protons. And so that part can't be acidic in and of itself. But we have these three other protons. And so to predict which one is more acidic, we first have to think about what's our product when we would remove any one of them. So if we took a base and deprotonated from here versus here, we would get three unique products, right? If we took away this orange proton, we would be left with a lone pair and a negative charge on this first carbon. If we took away this purple proton, we would have a negative charge on that carbon. And then if we were to take away the blue proton, our negative charge would be over there, right? So before we can analyze which proton is going to be more acidic, we have to think about what the products would be. And so when you're first starting off, it's a good idea to go ahead and just draw all of the possibilities, and then we can use our rules to compare which one of these would be the most stable conjugate bases and thus the most acidic proton, right? So let's just go ahead and do another quick example of this. Right, and then again, we're going to add some kind of base here, and we're going to deprotonate one of these protons. And we want to predict which proton it's going to be. Again, we have to think about what protons are available. There's a proton over here, one over here, one over here, and then, of course, the proton on the oxygen as well. There's several carbons, this one and this one, that don't have any H's. And so they can't be sources of acidity because they have no H plus to donate. And so we can think about what our products here would be. Again, we can draw a reaction mechanism, the base taking away the proton, and then the carbon-hydrogen bond breaking and leaving a lone pair. Or in the case of this green one, right, we're breaking an oxygen-hydrogen bond. And so then you can go ahead and draw all of your products, right? If we deprotonate this orange one, be left with a negative charge right there. If we deprotonate the purple one, our negative charge would be in the center right here. Deprotonate the blue one, be left with a negative charge there. and then deprotonate the green one, we'd be left with a negative charge there, right? So which proton is going to be more acidic? The first step is to draw all of the possibilities, right? All of the conjugate bases. And then once you've drawn the conjugate bases, you can go ahead then analyze them. You can do the same with bases. So for example, we could draw this compound right here. And then what we're going to do is add some kind of acid to it, right? We're going to add an H+. And so in order to make this bond here, in order to pick up this H+, we need a lone pair to do so. If we think about these carbons, all of these carbons, none of these have a lone pair. And so they can't be basic, right? Because they have no lone pair with which to grab this proton. However, this oxygen over here, that has a lone pair. And same thing with this negatively charged carbon, that also has a lone pair. And so if we're going to analyze which one of these sites are going to be more basic, we first have to think about what could our potential products be. So we're left with either this, where the negative charge now remains on this carbon, but now our oxygen is protonated. Or we could leave the oxygen deprotonated and protonate our carbon over here, right? We don't have to draw it, but now we know that there's an H there. So again, when you're talking about acidic or basic components, you want to think about what the products are going to be. And before you can think about what the products are going to be, you actually have to draw them. And then once you've drawn them, we can then analyze them according to our criteria.